Alright, so this video is about LeChatelier's principle. This is one of the guiding principles for equilibrium. So when a reaction reaches equilibrium, it will stay at equilibrium until something happens to disrupt the equilibrium. Once the equilibrium is disturbed, the reaction will go back toward equilibrium, basically undoing whatever disturbance occurred to it. So what do we call a disturbance to a reaction? A disturbance in a reaction is anything that can change the concentration. So adding more reactant, removing reactant, adding product, removing product, or even changes in temperature or pressure if we're talking about gases, changing the volume of the container for a gas reaction. All of these things can be disturbances to the equilibrium. So we're going to look at each of these types of disturbances and determine what happens. So let's say we have a reaction A plus 2B creates C plus D. In this reaction, if A, B, C, and D are aqueous or gas components, altering any of those concentrations will affect the equilibrium and cause the reaction to shift to reach equilibrium again. So let's say that we add reactant A to the reaction. Adding more reactant will cause a Q value to be greater than the K value. And that will cause the reaction to shift. Alright, so adding more product will change the Q value, so the reaction will shift toward equilibrium. So let's say we add A. Adding a reactant, is going to cause the reaction to shift toward the products. We're going to have to use up some of the excess reactant in order to make more products to get back to the equilibrium ratio. Removing A, or taking away the reactant, will cause the reaction to shift back to the left toward reactants to make up for what was lost. The same kind of things happen when we mess with the products. So if we add a product, if we add C or D, the reaction will shift back to the left to use up the excess product. If we remove C or D, the reaction will move toward the products to replace what we took away. Alright, we can see this also when we measure the concentrations. So in this reaction we have nitrogen and hydrogen gas creating ammonia gas. So when we start out, our reaction is at equilibrium. We can see the different concentrations of N2 and H2, which are our reactants, and our concentration of ammonia. So we have constant concentrations while our reactions are at equilibrium. Alright, now we're going to disturb the equilibrium by adding ammonia. So we're going to spike in ammonia here, so we see the concentration jump up dramatically. And then we see the concentration start to gradually decrease. So the increase in ammonia made the reaction shift back toward reactants, and now it's using up that excess ammonia, so the concentration is going down until it reaches equilibrium again. Now when the ammonia was spiked and the reaction went back to reactants, our H2 concentration starts increasing until it reaches equilibrium. And our N2 concentration also increases until it reaches equilibrium. Alright, so we can see how the reaction shifted using up some of the ammonia to create more N2 and H2. So adding a product, adding ammonia, caused the reaction to shift to the left, and we can see the changes in concentration that are affected. Now also notice that I have a larger change in H2 concentration compared to N2, and this is because of the stoichiometry. I am creating 3 times as much H2 compared to N2 when the ammonia breaks down. So let's think about this in terms of Q and K then. If I have a disturbance, I know that Q is going to be changed. So let's look at an example. I have PCl3 and Cl2 creating PCl5. If I start out with these initial amounts of my reactants and products, I will get a certain KEQ value. And this KEQ value reflects the equilibrium constant, because these are the concentrations at equilibrium. But now let's say I increase the pressure of PCl3 by 0.1 atmospheres. So increasing the 0.12 to 0.22 means that I have disrupted the equilibrium. I'm no longer going to be at my K equilibrium ratio. Because I'm adding a reactant, my Q is actually going to be less. Alright? So this means my reaction is going to have to go toward product formation to reach equilibrium. Or that means I have to use up some of the excess PCl3 to make more PCl5. When I do this, not only do I have to use up PCl3, I have to use up some of the Cl2 to make my product. So we can think of this as a balancing act. If we think about having scales that balance between reactants and products at equilibrium, and then something happens to shift our balance. So adding more reactant causes that side to go down and the other side to come up. And we can only balance it out by taking some of the reactants and turning them into products until we get our balance back or our equilibrium back. So let's try out a few examples. CO plus 2H2 produces CH3OH, or methanol. Alright, if I add methanol to my reaction at equilibrium, what should happen? So adding a product will cause my reaction to shift toward the left, or toward reactants. So my methanol will go down, my CO and H2 will go up. What if methanol was removed? So instead of adding it, what if I take it away? Removing the methanol will cause the reaction to shift to the right toward the methanol, because we have to replace what was taken away. So our reaction will make more product. What about adding CO? If I add a reactant, my reaction will shift to the right to use up the excess reactant to make more product. Alright, so that's what happens with concentration changes. Let's look at temperature changes. If I change the temperature of the reaction, we know this affects the rate. Okay, we've already seen how rate affects the reaction. Temperature affects the rate of the reaction. But it also affects the equilibrium. Remember, KEQ is only true at given temperatures. So if I change the temperature, my KEQ will change. And the way it changes is based on whether the reaction is endothermic or exothermic. So we have to know whether we have an increase in heat going into the reaction or we have heat released from the reaction. We can treat the heat of the reaction like it's a reactant for endothermic reactions or a product for exothermic reactions. So we're only doing this to try to understand the concept. Heat is not only on one side or the other. So that's my warning. You cannot change the temperature of the reactants and not the products. You're changing the temperature of the whole reaction. But whether you have endothermic or exothermic reactions will affect which direction the reaction moves in. So let's look at endothermic first. If I have a net increase in heat going into my reaction, I can think of my heat as a reactant. So increasing the temperature would be like increasing a reactant, and it will shift to the right. If I decrease the temperature, taking a reactant away, my reaction will shift to the left. The opposite's true for exothermic. If my heat is now on the product side as heat is being released, increasing the temperature will cause the reaction to shift left. but decreasing the temperature will cause it to shift to the right and make more products. So let's look at these two equations. Let's say I work in a lab that wants to produce HCl. So it's my job to make as much HCl as possible. I have these two reactions that I can use. So if I look at the first one, B2H6 goes to 6Cl2, HCl is a product, and I have a negative delta H, so this is an exothermic reaction. So what should I do to the temperature to get more HCl? If I want my reaction to go toward product formation to make more HCl, I need to decrease the temperature because this reaction is already producing heat. So I need to take heat away so that it will go toward the products. The second reaction is endothermic. My HCl is still a product, but because this is an endothermic reaction, I want to increase the temperature so that my reaction will shift toward the product side. And we have a familiar equation that goes along with calculating K equilibrium at temperatures. This should look very familiar because this is similar to the Clausius-Clapeyron equation. It's similar to the Arrhenius equation. And this one is called the Van 't Hoff equation, but it's the same idea. We're looking at a ratio of KEQ values, changing based on the delta H of the whole reaction, using our gas constant R in terms of energy units, and our differences in the reciprocal temperatures in terms of Kelvin. So let's say that we have a delta H value of 111 kilojoules per mole for a reaction, and K is 1.25 at 25 degrees Celsius. We want to know what is the new K value if I change the temperature. Now if we look at what we have, since our delta H of the reaction is positive, we have an endothermic reaction. So what should happen when I raise the temperature? What do we expect to happen to K? So think about what we said before. If it's endothermic and I raise the temperature, which direction is it going to move? Raising the temperature should make the reaction move to the right, toward product formation. If I'm making more product, my K equilibrium value is going to increase. Alright, so for an endothermic reaction, increasing the temperature is going to cause K to go up as well. So compared to 25 degrees Celsius or 298 Kelvin, having a temperature of 850 should be a dramatic increase in the K equilibrium value. Alright, so we've looked at concentration, we've looked at temperature changes. The last one we want to look at is pressure changes. And this can be changing pressure in a couple of different ways. But remember, this only affects reactions that are in the gas state. Gaseous reactions can have changes in pressure. If it's an aqueous reaction, we can't change the pressure to affect the equilibrium. Alright, so what's going to affect the pressure? So I can change the concentration of any gaseous component. So I can add or take away reactant or product, even when they're a gas. Alright? But adding an inert gas, and this means adding a gas that is not part of the reaction and will not affect anything in my reaction, does not affect the equilibrium. It will not cause it to shift toward left or the right, because it's changing only its partial pressure or the total pressure of the whole reaction. So the partial pressures of the reactant and product gases remain the same. But adding a gas component of the reaction will reshift the reaction, and we'll look at that in a minute. The other thing that will affect the pressure is changing the volume of the container. So if I have a gas reaction and I try to put the gas reaction into a smaller container, that will change the pressure, and that will cause a shift. Conversely, if I put it in a larger container, it will change the pressure and cause a shift. So which way is it going to shift? So let's look at our two options, increasing pressure or decreasing pressure. If I increase the pressure of the reaction will shift to minimize the number of gas molecules. So it's trying to lower the pressure back down by getting rid of some of the gas molecules. So it will shift in the direction of the least amount of gas molecules to try to minimize them. If I lower the pressure and I give it more space, it will try to maximize the gas molecules in order to take up as much room as possible. So again, trying to go back to the state it had before. So it will move in the direction of the greater number of gas moles. So let's try these. PCl3 plus Cl2 creates PCl5. What's going to happen if I increase the pressure? So if I increase the pressure on this reaction, I can see I have 2 moles of gas on the left, one of each of these, but only one gas molecule on the right. So increasing the pressure, it wants to minimize the gas moles. So this one's going to move to the right, where there's less gas moles in the product. Second example, 2NO2 goes to N2O4. What happens if I decrease the pressure? So in this example, I have 2 moles on the left, 1 mole on the right. So decreasing the pressure, it wants to try to maximize the gas moles to take up more space. So this one would shift to the left, where I have more moles of gas. Alright, let's look at one that has a solid. NH4HS solid on the left produces 2 gas molecules, NH3 and H2S on the right. So what happens if I increase the pressure of this reaction? Since I have no molecules of gas on the left, producing more reactant will have less gas moles compared to my 2 gas moles on the right. So increasing pressure, I want to minimize gas moles, so it's going to go back to the left where I have no gas moles for the reaction. Alright, and the last thing to mention about equilibrium is catalysts. We talked about catalysts previously as agents that help increase the rate of a reaction. But what do they do to equilibrium? Since they are affecting the rate of the reaction, could they be disturbing the equilibrium? And the answer is no, only because catalysts affect the rate of the forward and the reverse reactions. So remember, you can't use a catalyst to affect one or the other. It's going to affect both directions. So a catalyst just speeds up the rate of the reaction. It allows you to reach equilibrium faster, but it does not change what equilibrium is. It doesn't cause the reaction to shift to the left or right. It just speeds up the overall process so that you achieve equilibrium in an earlier time point. Alright, so here's the summary for LeChatelier's principle. If I change the concentration of reactants or products, it will cause the equilibrium to shift. But it does not change KEQ. I can get a Q value and then determine which direction it would go in. If I change pressure or volume for gas reactions, equilibrium will shift if I have gas. If I don't have gas molecules, it will not shift. But KEQ does not change. Changing the temperature will shift the equilibrium based on whether it's endothermic or exothermic, and it changes what KEQ is. It changes the numerical value. And then finally, having a catalyst in the reaction does not shift the equilibrium one way or the other. It just speeds up the overall reaction, and it has no effect on KEQ.